experiment modeling or methodology. Just few words because we change the progress of the seminar. You can use the yellow hand at the bottom of the screen to ask question at the end of the presentation, and I will turn on your microphone. But during the presentation, you can use the chat to ask question, and I will read the question to the speakers, to the speaker. Okay, so it's your turn, Romain.
Thank you very much. Thank you very much for having invited me for this seminar. I'm very happy to be here. And so this is a presentation called A New Shifted Lognormal Distribution for Mitigating Exploding Implicit Prices in Mixed Multinomial Logit Model. I might not know most of you, so my name is Romain Crastes. I'm from the University of Leeds. I'm working at the Leeds University Business School at the Center for Decision Research, and I'm also affiliated to the Choice Modeling Center. And this work today has a lot to do with choice modeling. So I will first introduce to those of you who don't know what stated preferences and choice modeling are. I will just give a very short crash course. It's going to be just a couple of slides. Most of you are probably familiar with it. Then I will expose what I mean by the exploding implicit price problem, and I will show which solution I propose in this paper. I will then present the framework for empirical testing, which shows how the proposed solution actually works in practice. We'll discuss results, and there will be a couple of final remarks. So choice modeling, because I know that this is an economics seminar, not necessarily an econometrics or choice modeling seminar. So by choice modeling, this is a quantitative method. This has largely to do with econometrics, and this is based on the idea that a large share of behavior is a result of choices. In this context, we are interested in analyzing choice behavior for appraisal and demand forecasting. That's not the only uses of choice modeling. That's the uses we're going to focus on today. We are going to focus on explaining individual choices, but one could also model company choices, group choices, joint choices, whoever the agent is. And in the context of today, choices are going to be discrete, but in general, you can use choice models to model both discrete and continuous choices, such as what do I buy and how much of each. So it has applications in a wide range of disciplines, such as transport, health choices, which treatments do patients prefer, for example, environment, so non-market valuation, for example, how much do we need to, how much do people want to pay for conserving some environmental assets, education and marketing, which products do people prefer and which features do they prefer. In this work today, we only use stated preference data, which come from what most of you might know as discrete choice experiments. But this work is relevant for revealed preference data too, anything which has to do with the modeling of preferences really, and the valuation. So I'm going to call this stated preference surveys, but you might know this again as discrete choice experiments. And this is a technique which is very widespread to assess preferences of agents in a hypothetical context. And a very broad definition would be that this is a survey method where you present agents with or decision makers with a set of hypothetical scenarios in a controlled environment, and you ask them which alternatives do you prefer as a function of the features of these alternatives. And this is very useful to derive, for example, in non-market valuation, willingness to pay estimates. But for example, this is what can be used in transport to derive value of travel time survey, which informs policymaking in transport. This can be criticized because it's sometimes lack of realism or respondents aren't incentivized to answer the survey truthfully. This isn't something which we're going to discuss much today. There is also one issue with the fact that this is both easy and difficult to design at the same time, because nowadays you've got softwares which are such as Engine, which are very good for generating surveys. However, that doesn't mean that the survey itself is going to be good. It's easy. It doesn't require programmation anymore, or not much of it. But it's still complicated to design at the same time. So I'm going to take an example from my PhD thesis, which is, I think, 8 or 9 years ago. This data has been collected. The data which we are going to use today isn't going to be relevant for, I mean, the models we're going to estimate today aren't relevant for policy making necessarily. This is just to show how the method works. So it doesn't matter how new the data we use is. And so this was a survey which had roughly 450 respondents, okay? And where each respondent faced 6 choice tasks. And each choice task was composed of 3 alternatives, which I'm going to show in a second. And it was a face-to-face survey, which was aiming at identifying preferences for different policies aiming at reducing floods in Normandy, which is a region of France, which you might know if you're interested in the Middle Age. This is close to Rouen, where Joan of Arc got caught by the English and burned. Right, so this is what your typical stated preference survey looks like, at least in non-market valuation, okay? We've got a set of attributes which are all methods for mitigating floods, okay? So you could, what I call agriculture is you could build more hedges and set farms and fields in such a way that it retains water. You could improve infrastructures, build more dams and things like that. Or you could communicate more about it to prevent, to incentivize people to protect their houses and so on. And so each attribute can take 2 levels. Yes, it's featured in the policy package, or no, it's not featured. And of course, there is a cost. Okay, and people face 3 alternatives, alternative 1, 2, and 3. The third alternative being the status quo. And they asked, which alternative do you prefer? So you've got the alternative 1, which features agricultural methods for mitigating floods and more communication. It's going to cost you 32.5 euros per year. Or the method 2 is only about infrastructures, and it's going to cost you 25 euros per year. So respondents indicate which alternative they prefer, and then you move on with a new set, with a new choice set. And you use these to derive the choice, to derive the utility and preferences of people, and ultimately willingness to pay. So this is what my utility functions look like. We've got the utility for alternative 1, which is based, which is basically a constant, plus the beta, that is utility derived for agricultural for protecting against flood via agricultural methods, and so on with the other attributes, plus an error term. And this is the same, but with different value for the axis for the other alternatives. Okay, one of the constants needs to be normalized to 0, usually the third one, which corresponds to the status quo. And so if you assume an error structure which leads to a multinomial logit probability, you can derive the probability of selecting alternative 1 based on the logit formula. And this allows, given that this is random utility maximization, this allows for welfare estimates, which is corresponds to the willingness to pay of people for each one of the attributes. And this is basically dividing beta for agriculture, for example, by the beta for the price. That's how you derive willingness to pay estimates. But that's not all. So the standard modeling strategy, the basic one, I would say, is the multinomial logit model, where one assumes that preferences are homogeneous across respondents unless social demographic variables are introduced in the model. And so the preference of people is, of all the people in your sample, is considered to be beta agree in that case. But that usually results in poor fit. That is, your model doesn't explain well the choices made by respondents. So that's why most choice models move to the mixed multinomial logit, where it is assumed that preferences vary randomly across respondents, usually following a parametric distribution. And so here, for example, given that people might either like or dislike changing agricultural practices to improve the protection against flood, I can specify beta agri as being normally distributed, okay? So it's not just a point estimate anymore. This is a mean and a standard deviation multiplied by standard normal draws. So that would give me a normal distribution. And I assume that the preferences of people in my sample are normally distributed for this attribute. But what about the price? So here it is assumed that, in general in the literature, it is assumed that people dislike an increase in price, okay? So the marginal utility for the price attribute is negative. The more the price increases, the less happy you are, all else being equal, okay? Makes sense in economics. And so the price can be, if you want a price to be randomly distributed, you can specify your price as log normally distributed. So that's basically minus exponential of mean plus standard deviation of a normally distributed variable. Okay. And that gives us here a normal distribution, and here that gives us the log normal distribution, negative log normal, okay, because it's constrained to be negative. We don't want people to derive a positive utility for a price increase, okay? It doesn't make any sense. And it's not the only issue with it, as we're gonna see in a second. So that's the typical output you get from your model. Here I've got my multinomial logit model, which has the poorest log likelihood. Okay, it's much lower than the log likelihood for the rest of the models. You can also check the AIC and BIC stats as well as the R square. And it doesn't have randomly distributed preferences. So all the betas are point estimates, variant distributions. And here we can see that the model which fits the data the best is the model where the price is log normally distributed. Okay, then I just derive welfare estimate. So I divide, for the multinomial logit model, I derive my beta for agriculture, for example, by beta of the negative of beta of the price. For the log normal model, it needs to be simulated, okay? So the way it's done is that I simulate 10,000 or a million points from the distribution of agriculture estimated by the model. And I do the same for the distribution of price, and I divide one observation by another, and I just do the average of all of that. Okay, and what do I find? I find that for the multinomial logit model, if we look at agriculture, for example, the marginal willingness to pay for an improvement in agricultural practices is 24 euros per year. For the fixed monetary attribute model, which it's only 18.82. And okay, what do we see for the log normal, for the model with the log normally distributed price? This is 185 euros per year. Despite the fact that the highest price bid in my experimental design, that is the highest amount of money people could pay, was 32.5 euros. So what's happening here? And so, whoa, why is my best fitting model giving me willingness to pay estimates which are between 7.34 and 10 times higher than the other models? That's a bit high, okay? That's because of the exploding ratio problem. And then, yeah, I'm being a bit overly dramatic with the picture, but it's a problem. So the issue is that the log normal distribution has a point mass near zero, okay? And so when you calculate the ratio of a normal distribution on a log normal distribution, when you simulate the resulting distribution, that can lead to a very few large values. Why? Because remember, this distribution on the right, the negative log normal, has a point mass near zero. So it can produce a set of very small values in the denominator of the willingness to pay calculation. And these values are going to have a strong influence on mean willingness to pay estimates. And of course, this captures very low sensitivity for the cost in the data, but that's also making your welfare estimates unusable for policymaking because they're way too large. But there are some solutions in the literature. And one of them is to just assume no random heterogeneity for the price attribute, but this is implausible. Different people have different sensitivity for the cost. Even when you account for the income, there is still some random heterogeneity remaining. And usually this approach leads to a much poorer model fit. So the model which you get has reasonable willingness to pay estimates, but it's not the right model, the right model being unknown. There is the willingness to pay space approach, where instead of estimating the utility for each non-monetary attribute and deriving the willingness to pay from the utility, you estimate the willingness to pay for each attribute, and you can, if you want, derive the utility. What for the non-specialist, what this allows you in a sense is to give you a different range of distribution possible for the willingness to pay for each attribute. And in this case, that would allow me to specify my willingness to pay for, let's say, agriculture as normal, instead of specifying it as the ratio of a normal and a log normal distribution. Okay? The thing which is great about this method is that it, again, allows you for different distributional assumption. And it prevents the exploding ratio problem, because you don't have to compute this ratio anymore. You estimate directly the willingness to pay distribution. However, in some contexts, and especially in non-market valuation, it might lead to a poorer fit. But this is, again, very context specific, okay? It seems to work better in transport, in my experience, where, for example, when you calculate value of time with a preference-based model, since both time and cost are bad, they're both log normal, negative log normal. So when you do the ratio of two negative log normal, that doesn't make much difference with a model in willingness to pay space where time is already specified as negative log normal. So that varies. But you could also, instead of using a negative log normal distribution for the cost, you could use a negative log uniform distribution. This is suggested by Hess et al. But at least in non-market valuation, and we're going to see this in a second, it doesn't fit as well as the log normal distribution. So the fit of the model is not as good. And this is still prone to the exploding ratio issue, because this distribution doesn't have such a big point mass at zero, but it still has a point mass near zero, okay? And then there is an approach which isn't popular at all, but which I quite like myself, which is the cost-income ratio approach, where one uses a negative log normal distribution for the price, but shifts the denominator of the ratio away from zero using data. So where someone adds an interaction variable, which is the price of the good divided by income. But this is not non-standard, because this isn't a standard interaction variable. This is a division instead of multiplication. This needs additional data, and this is not necessarily well behaved. Okay, sometimes you get a cost-income ratio which isn't of the right sign, and then that doesn't help with shifting the denominator of the ratio away from zero. So what's the point of this research then? Well, the point of this research is to suggest that the models which don't fit the data well suggest that they aren't the right model to use. Again, we don't know what the right model is. But the models which fit the data better or well might lead to unusable welfare estimates, because they're way too large. And that's bad too. So how can we get both good fit and reasonable willingness to pay estimates? And this is something which has been a relevant research question for a while in the literature, especially around the time where willingness to pay space model was suggested. And especially Train and Week say that research is needed to identify distributions that fit the data better when applied in willingness to pay space, and or provide more reasonable distributions of willingness to pay when applied in preference space. And so here, what I suggest in this research is to use shifted log normal distributions. And more precisely, this is an attempt in preference space to shift the denominator of the willingness to pay ratio away from 0. This isn't a distribution that has received much attention in the choice modeling literature. This has been originally proposed by, as far as I found, Sengal and Biswas in 1970, but with application in hydrology to model, I think something related to floods, actually. And this is a very simple thing to do. This simply consists in adding a third parameter, the shift, to a positive or negative log-normal distribution. In our case, that's going to be a negative log-normal distribution, of course. And so we introduce this new parameter, which is kappa.
Excuse me, Romain.
Yeah.
I have a question.
Sure.
What does mean an unusual welfare estimate? It's a question from Lionel Rago. What does mean an unusual welfare estimate?
Unusual welfare estimate would be welfare estimates which are well too far away from what one would expect given some values presented in the stated preference survey. So for example, if you ask respondents to choose a set of policies and you have a series of price levels for each policies which range from, let's say, 0 to 50, okay? But if you derive willingness to pay estimates from your model, which are 500, that's just too far away from the values shown to the respondents to correspond to something which, how can I say, this means that either you have a problem with your model, so you're using the wrong distribution, and that causes, for example, the exploding ratios that I mentioned, or that means that your respondents are too price insensitive. Okay, they have made the choices without caring about the price much, which means that your stated preference survey has been poorly designed. Okay, which means that people have answered without without really putting any weight to the price, which they should. Okay. So let's move on. So the thing is, the shifted log-normal distribution has limited use for choice modeling, okay? Because first of all, it has issues with local optima. So when you estimate your model, I have tried a bunch of specifications, and the model had a lot of trouble converging. But that's not the main problem. You can always have good starting values with your model and so on. The real issue is that the new parameter kappa can be positive, okay? It can be either positive or negative, but if it's positive, you have a distribution for the price which spawns on both sides of 0, okay? And that means that if you are doing the ratio of your non-monetary parameter and your monetary parameter, if you're doing the ratio of distribution, the resulting willingness to pay distribution has no moments, okay? It means that you cannot calculate the mean. And so that's a problem, because if you want to do policy making, you need mean willingness to pay estimates. You can't, you can give it a try, but constraining kappa to be negative has undesirable effects, because if I, for example, use minus exponential of kappa minus exponential of the rest of that equation, kappa is going to reach very small values. So exponential of minus 25, for example, which is nearly 0, in an attempt to reach a positive value, but it can't because it's constrained. So your model is not going to work. So that leads me to suggest that we need to find a shifted distribution with more desirable properties. And in this paper, we suggest we have these two propositions. I first suggest the kappa shifted distribution, okay, where beta price equal kappa minus exponential of sigma price multiplied by normal draws. And this is an attempt to constrain the mean parameter of the log normal distribution to 0 to help the shift reaching a negative value in most cases. So we are putting most of the heterogeneity in the mean, captured by the mean, in this kappa. The second method, which is inspired by Henscher and Green's constrained triangular distribution, is to shift the log normal distribution by its own mean. Okay, so instead of estimating a new parameter called kappa, we use minus exponential of mu price, minus exponential of mu price plus sigma price multiplied by normal draws. So in essence, we reuse the same parameter twice to define the preferences for the price. And as we can see, they are both negative exponential, meaning that they cannot reach a value which is positive. And as we will see in the following distributions, this is going to prevent the distribution of the price to reach values which are too close to zero in most cases. So here I have the log normal distribution, kappa log normal distribution, and mu log normal distribution, all negative, and they are all standard. So they are all with mean or shift 0 and standard deviation of 1. And the first thing you can see is that when the shift of the kappa log normal distribution is equal to 0, well, this is completely the same thing as the log normal distribution, okay? While my mu shifted log normal distribution is shifted away from 0 already. And then I can show different distributions. Now, if kappa is equal to -1 and all the other distributions keep the same characteristics, now this is the kappa shifted log normal distribution, which is the same as the mu log normal distribution. And now we just try different values, and we can see that when the mean, remember that this is log normal, so it's exponential of a negative number. So when the mean gets lower, we can see that the log normal distribution has a point mass which gets closer to 0, but the mu shifted is still has a point mass which is away from 0. And we can see that the kappa shifted is even much more away from 0 than the two other distributions. And that's what we want. We want this distribution to be away from 0 to avoid the exploding implicit price problem. And that's just other illustrations with different values, but you get the idea. So how are we going to show that this is useful for choice modeling? We are going to compare the three proposed shifted distributions, so the three parameters log normal, the kappa shifted and the mu shifted, to all the other standard approaches we have mentioned already. So the multinomial logit, the approach where there is no random heterogeneity for the monetary attribute, the log normally distributed price, the log uniform price, and the willingness to pay space approach. We are going to use 10 data sets, and so that's going to be 8 models per data set. So we estimate 80 models in total using 2000 MLHS draws to approximate the distributions in all cases. Model estimation has been carried out using Apollo. This is a package developed by my colleagues Stefan Hess and David Palma in Leeds. I recommend using it for estimating your choice models. And if you want the code for the models estimated in this paper, they're available upon request. So what we're going to do is to look at the goodness of fit of the model, as well as willingness to pay estimates, to see what is the effect of introducing this shifted distribution. And then we're going to carry a meta-analysis of willingness to pay estimates to measure the overall effect of the shifted distributions on willingness to pay estimates with respect to the classic distributions. We are going to compare the willingness to pay distribution using kernel density test to see how similar they are. And if there is time, we are going to talk about out-of-sample goodness of fit, but that's not very essential for this talk. So this paper goes beyond the typical preference space versus willingness to pay case study found in the literature, in the sense that we use 10 data sets. So there is a lot of evidence. So this is 10 stated preference data set coming from published studies or government report on a large range of market and non-market choices. So in addition to the Normandy flood protection, there are lots of different case studies related to coffee choices in Nantes, forest management in Poland, endangered fish species, the funding of Warsaw theaters, car choices, chicken choices, and improvement of water quality in Germany. I'm not going to describe all these data sets in detail because there is no time. Okay, I'm just going to take the example with one attribute per data set, just for the sake of readability. But what I'm going to show you first is that each data set has been selected because they have different sensitivity for the monetary attribute. So what this means is that depending on the data set, people were more or less sensitive to the price attribute. And what the literature says is that the alternative with the highest bid should not be selected in more than 5 to 10% of the choice situations where it is present. Otherwise, that suggests that your respondents are actually price insensitive. And this is, and we have selected data sets which have in fact a percentage of choices selected higher than 10% for the highest bid, because we want to test the effect of these badly behaved data on the exploding implicit price issue. And so this is a distribution of, this is a cumulative bid acceptance curve. So here you can see the monetary attribute level, okay? And the higher means, how can I say, all these different data sets have different price levels, okay? One has 13 price level, another one has 7, and so on. But what one needs to look at is the percentage of respondents who have selected the highest price range in each data set. And here we can see that most of our data sets are well behaved, apart from the chicken data sets, for which nearly 25% of the respondents have selected either the highest or the second highest or the third highest price range. But the highest price range here being 5.5 euros for improving chicken quality. But the second highest is 5 and the third highest is 4.5. So they are very close to one another. It means that people are very price insensitive. The other concerning data set is the fish conservation data set, where 25% of the respondents have selected the highest price bid, which suggests price insensitivity. The rest of the data sets are fine. So let's
Excuse me. I have a question.
Yeah.
Is it not a problem to, it's Martin Koning, which has a question. It is not a problem to use some data from subjects, some studies, so different in...
No, I don't think that's a problem. Actually, I think that's the strength of the paper, because we just show how the proposed method performs in a wide variety of contexts. And if you use meta-analytical methods anyway to check your result and to measure the effect of the proposed modeling approach on willingness to pay estimates, you can just use one constant per data set to capture the effect of the specific survey on results. So I wouldn't see a problem with doing that. But I'm happy to further discuss this at the end of the presentation.
Thank you.
Okay, so moving on with this, what are our results? So the mixed models in preference space, all of them, apart from the one where the price attribute is set up as non-random, outperform the willingness to pay model in all 10 cases. The lognormal model is found to be the best fitting model in 7 cases out of 10. And the shifted lognormal distribution with 3 parameters is the best fitting model in 2 cases out of 10. And the kappa shifted model is the best in 1 case out of 10. But however, none, or at least very few of these models are great for policy making. Why? Because the lognormal model yields very large willingness to pay estimates in a vast majority of cases. So it suffers from the exploding implicit price issue. The 3 parameter shifted lognormal and the kappa shifted model failed to deliver moments for willingness to pay distribution in 8 and 3 cases respectively, meaning that the shift parameter is positive for these models. So you can't have moments for your willingness to pay. However, the mu shifted model is extremely close to the best fitting model in all cases. The difference is marginal in all cases, and it delivers moments in all cases. So general trends about willingness to pay are better assessed via meta-analysis. So I will focus on a few case studies to show the usefulness of the method. So here comes the results. So this is result for the Normandy flood protection survey, okay? And so this orange bar is my willingness to pay estimate for a given attribute, which is in that case, improving infrastructures like dams and dikes and so on. And this red bar is the highest price bid in the stated preference design. And these blue bars here correspond to the goodness of fit of the model, that is the BIC. And the BIC is the lower, the better. And so what can we see? We can see that the log normal and the log uniform all have very high willingness to pay measures, okay? The highest bid again is 32.25. And here I can find 184 euros per year and 59 euros per year. On the other hand, the willingness to pay space model gives 14 euros per year and the non-random price 18 euros per year. The multinomial logit model, which doesn't assume anything regarding the distribution, it's just point estimate, gives me 26 euros per year. Now, let's look at the mu shifting model, which again has the same number of parameters, and the shifting model, by the way, have the same number of parameters as the log normal and log uniform model, but instead of very high values, they give values which are actually in line with the multinomial logit model and a bit higher than the willingness to pay space approach. But the fit, the goodness of fit is much better than the willingness to pay space approach. For the mu shifted distribution, for example, it's 2,791 instead of 3,109, which means that the mu shifting model fits the data much better than the willingness to pay space approach. And if you look at the log normal BIC, it's very close to the mu shifted one, okay? But at the same time, the mu shifted one achieved these good results without having absurd willingness to pay estimates. And this is something we observe in quite a few cases, okay? Now this is a data set about restoring and conserving Polish forest called I can't pronounce it very well, I apologize. And again, this red bar is the highest bid, which is 100 zlotys. And what we find is that the log normal model gives us a willingness to pay for improving the naturalness of the forest of 144 zlotys. And so this is above that range. The log uniform of 82 zlotys, which is a bit high with respect to the other model. While the shifted, the kappa shifted and the mu shifted distributions give values which are respectively 40 and 50, which are very close to the one given by the willingness to pay and multinomial logit model, while at the same time, again, fitting the data much better. We observe very small differences when it comes to the car choice, but again, we find the same trend. The mu shifting model yields and the shifted model yields much lower willingness to pay estimates than the log uniform and the log normal, while at the same time having the similar fit and better fit than the willingness to pay space approach. And even in the case where the respondents have a very low preference for the price attribute, so they don't really care about the price. That's the chicken meat choice. That's a data set with more than 25% of the respondents selecting the highest bid or close to the highest bid. We can find that the log uniform and log normal approach, but especially the log uniform, give extremely high willingness to pay estimates, okay? The highest bid being 5.5, while the mu shifted also being above 5.5 gives very reasonable willingness to pay estimate, even when respondents don't really care about the price. Obviously, these values have a tendency to explode a bit with respect to the willingness to pay space approach because of distributional assumption. But at the same time, the mu shifted approach, again, fits the data much better. So in conclusion, I'm going to skip that because there is no time, but that's not essential. That's something I've done this morning. In conclusion, what we can say is that we propose a specification which has virtually the same fit as the log-normal approach, while at the same time giving much more reasonable willingness to pay estimates. And this is confirmed by a meta-analysis where we estimate a model which is the log of the marginal willingness to pay for all the attributes of all the data sets considered. So that's 414 observation. Okay, so that's one attribute per model. And that's 8 model per data set, and each data set features between 3 and 16 attributes. And so we basically make a log linear regression which seeks to capture the effect of the modeling approach on willingness to pay estimates, all else being equal. So we introduce constant to capture the effect of each data set. So that's a very basic meta-analytic approach. And long story short, what we do is that we use either all observations or an approach where we remove the 2 data sets where respondents are price insensitive. And what we find is that the log normal and log uniform modeling approach give welfare estimates, willingness to pay estimates, which are significantly higher than the rest of the approaches. But we also find that the multinomial logit, the fixed monetary attributes, the willingness to pay space approach, and the mu shifted approach all give estimates which aren't significantly different from one another for the set of data used in this paper. So this is a very important result. These are marginal effects, and they need to be read as such. The log normal approach gives results which are willingness to pay approach, which are 6 times higher than the MNL, 7 times higher than the fixed price approach, 7 times higher than the willingness to pay space approach, and 4.8 times higher than the mu shifted log normal distribution. I haven't considered the kappa shifted distribution and the 3 parameter shifted distribution because they don't give moments in all cases. So I would like to put an emphasis on the mu shifted log normal distribution. At the same time, there is no significant difference between the willingness to pay space approach and the mu shifted approach, okay? So the confidence interval shows that they aren't that different from one another at the 1% level. So what do we conclude? We conclude that the mu shifted approach provides welfare estimates which aren't significantly different than the ML approach and the willingness to pay space approach, although the confidence interval is wider, while at the same time fitting the data as well as the log normal and log uniform approach. Of course, this can be case specific. I don't expect to find the same results with all data sets and other or in other fields, but for the set of data used, we can really suggest that the mu shifted approach is the best approach. And that's an example of the type of distribution that we get. And I'm gonna stop very soon because the rest is just more of the same. So the rest of the slides is more of me telling you that the mu shifted approach is better. So here, this is the distribution for infrastructure for the data set on flood risk. And we can see that the willingness to pay space approach gives a shape which is fairly different than the log normal approach, the log uniform approach, and the mu shifted approach. But in fact, we run some tests, and we run some tests to check what is the area in common between these distributions. And we find that the mu shifted distribution has 47% of its surface in common with the log normal distribution, while it has 67% of its surface in common with the willingness to pay distribution, meaning that the mu shifted approach has more in common in terms of the distribution of willingness to pay it gives with the willingness to pay space approach than the log normal approach, while at the same time fitting the data as well as the log-normal approach. So my general conclusion here is that the mu-shifted log-normal distribution is found to provide much more reasonable welfare estimates than the log-normal distribution for the price parameter for mixed multinomial logit model, around 80% lower on average. And the willingness to pay measures are very close to the multinomial logit or willingness to pay space values when the data is well behaved. At the same time, the mu-shifted approach fits the data as well as the log-normal approach and better than most competing approach, especially the willingness to pay space approach. And the three-parameter log-normal and the kappa-shifted approach are not suitable for deriving welfare estimates in all cases, but when they do, which is really left to chance on what kind of data you have, they perform well. So that's my general conclusion. I must once again say that although I tried this on 10 data sets, this must be case specific, okay? There are some cases where the best model, both in terms of how reasonable the goodness of the willingness to pay estimates and how good the goodness of it is, can be the willingness to pay space approach. Okay, that really depends on the data. But we find the mu-shifted approach to be a nice compromise anyway. That was my presentation, and I need to thank all these people: Olivier Baumet, Pierre-Alexandre Mailleux, Erland Enkersandorf, Mikolaj Tchaikovsky, Danny Campbell, Dan McFadden, Stefan Hess, Jürgen Meyerhoff, Kenneth Train, and Chiara Calastri, because they have either heard me rambling about this for months, or they read my paper and provided comments, or they gave data and provided assistance with fitting models and so on. So, or they just provided some thoughts on it. So their help has been acknowledged and very valuable. I'd like to also thank all my colleagues at the Center for Decision Research and at the Choice Modeling Center for having provided assistance with this work and with research in general. So thank you for your attention, and I guess there are 15 minutes for questions.
Thank you very much, Romain. I will give the floor to Michael Helling. We had ask a question. I will find him. Michael Helling, if you want to ask your question, you have your microphone is on.
Yeah,
I think so.
Can you hear me?
Yeah.
Yeah, perfect. So my question was the willingness to pay measures or values that you derive from your new method, or from the best mixed logit models in general, are not so far away from the willingness to pay derived by the normal MNL models. So if you just want to include a simple willingness to pay measure in your policy decisions, so why should you choose mixed logit approaches anyway?
Well, first of all, that might not be necessarily the case. Okay, the MNL is included out of to carry a very thorough sensitivity analysis, and also because you might need the distribution of the willingness to pay in your population to make better decisions regarding which amount is the most likely to be accepted by the population, or how is it spread out in the population. Or results from the MNL and the mixed logits can also change if you start including, I don't know, social demographic, for example, all these kind of things. So I would recommend to just because this explains the choices of your respondents better, to use the models with mixing. Because maybe I just got lucky with this data, okay? Maybe it gives different results in some cases. So that's what I would say. I would say that these models fit, the mixed model fits the data better. So I would generally use the mixed models for policy making. But I would, if I would do some very thorough policy making, I would of course try to add social demographic variables, income, and so on, which is something that I haven't done here because there is only so much you can do in such a meta-analysis.
Yeah, exactly. Okay. And you think one question maybe? You think it's reasonable to add some social demographic influences to the mean and the deviation of the mixed parameters? Does that make sense to you?
Yes, but that depends in which model you're talking about. For example, with the log normal model, I will try to get my slides back. Yeah. So if, for example, you take this equation here, especially in the context of the price, that might be relevant because since this is exponentiated, the mean of this distribution is influenced by both the value of mu price and sigma price, okay? So it makes sense to interact both with income. However, that's not something I would do in practice because that's going to make your model very hard to estimate, okay? I would only interact these values with mu, for example. But again, this is very case specific. From my experience, interacting variable with both mu and sigma makes your model very complicated to estimate. It sometimes has convergence issues, local optima, and so on and so on. But yeah, you can give it a try, definitely. But otherwise, I would just focus on mu. At least that's what I do.
Okay, thank you.
Thank you very much. Thomas Rossetti, I have a question for you.
Yeah.
Thomas Rossetti.
Hi. Yeah,
Hi.
I'm here. Thanks for the presentation. My question was, how can you interpret intuitively the beta cost when it is mu shifted?
Well,
like behaviorally, I mean, sorry.
Okay, I wouldn't, how can I say? I would interpret the distribution itself. I wouldn't necessarily interpret the shift, okay? I would reason in terms of the whole distribution. I would simply simulate it. So I would just simply do a quick simulation and oops. And look at the whole distribution rather than at the shift itself. So I would just plot the whole distribution, which would be, I don't know, something random exponential of -1 minus exponential of -1 plus 0.5 by d1 up. So I would reason in terms of complete distribution rather than just looking at the shift, because if I remove the shift, it's just going to give me a distribution which is anyway extremely similar, just a bit further away from 0. Okay, here that gave me the same one. So the shift itself doesn't have, at least in my opinion, any specific behavioral meaning. Only the whole distribution matter. At least from my point of view, I didn't investigate the behavioral implications of the shift itself. I reasoned in terms of whole distribution.
Okay, thank you.
Thank you very much. And maybe last question. Tej Decker, I want to ask you a question. Is it okay?
Yep.
You have the floor. Yeah, yeah, okay, thank you very much.
Thank you very much. Thank you, Romain.
Hey,
so I'm particularly referring here to your comparisons across the 10 data sets, where you're basically saying, well, I'm getting estimates of willingness to pay which are closer to the MNL and the normal density. But is that the right comparison that you're making? Wouldn't you be better off just comparing it against a more flexible distribution, like the Vosgrau and Wheeler type of?
Yeah, I mean, I see what you mean. I think this is expected of me to see, to compute how different it is from an MNL, okay? Just to show the MNL still being the baseline model without any distributional assumption, blah, blah, blah. However, and that's a very good question because I skipped that slide because there was no time for it. But when I compare, for example, I'm getting there. So that's not in the paper yet. have a data set which is the only one where I've done that and written it down, but there is evidence that it works for other data sets as well. I just haven't written it down yet. So I have this example with the not coffee machine data set where one attribute is, so this is choice between different coffee machine improvement. One of the attributes is whether you can pay by card or not. It's normally distributed because people either like or dislike it. And I did indeed try the Force-Geron Mabit mixture of normal, where I have a polynomial, I mean, of order 4, okay? You're familiar with this, right?
Yeah, yeah.
Yeah, and I compare this to the basic willingness to pay space and the mu-shifted model. And so what I find is that the mu-shifted still wins by quite a bit in terms of log likelihood. And if you consider the BIC, then it largely outperforms both models. At the same time, then you're right. In terms of mean, they're getting closer.
Yeah.
But it's much less parsimonious in parameter, in my opinion. And this is something I've observed with quite a few other data sets. I'm just getting the list of the data set just to completely address your question. I can send you the output, but that has the same trend for the Normandy flood protection data set, the Bielawa forest management, and the ecological value of Polish forest data set. I haven't tried with the rest yet, just because these take a while to estimate and so on. But the trend is the same as with the coffee machine data set.
Yeah, yeah. It's just to note that if the bias, if you're comparing it against the bias estimate, the comparison is not really.
No, I agree that this is not the most useful comparison, but I've been asked a couple of times during discussions with colleagues, how does it perform with respect to the basic MNL estimate? So that's why I focused on that. But in the final paper, I'm probably going to focus more on the Force-Geron Mabit approach. But yeah, that's a very good point. Thank you.
Is there any other question? If you want to use yellow hand to ask a question, I will give you the floor. So it is 5. Thank you very much, Romain, and thank you for your presentation, and thank you to all participants for the question and to participate to this seminar.
Thank you for your invitation and question. Thanks a lot.
Thanks. Romain, you can stay 5 minutes more if you want.